In this assessment, we illustrate the product of the reduction of an alkyne using sodium in liquid ammonia. We're not going to go through the whole mechanism here, but what we will point out is that an intermediate in this pathway, remember the way this reaction is going to work is that electrons from sodium, so sodium is going to spit out electrons. Electrons from that sodium are going to reduce the alkyne. And so we can draw it like that, push one of these electrons back to meet it, and one to go onto the alkyne carbon, is going to go through an intermediate that looks like this, a radical anion intermediate. So let me make sure we draw the right number of carbons, 2 carbons, and then the 5-membered ring. Double check that. Good. This intermediate is the intermediate that will ultimately add the protons to give us the alkene, but we show it because it can equilibrate between cis and trans. And trans being more stable, that's going to be where the reaction proceeds through. So it's going to proceed through the most stable intermediate here. And again, this is not meant to be showing a full arrow pushing mechanism, just pointing out the formation of this intermediate to justify one of the most important outcomes of this reaction is that we end up with a trans alkene. And so the final product is this. This is in contrast to had we used the Lindlar reduction where we add H2, both hydrogens add to the same face of the molecule at the same time to give a cis alkene. This one, the 2 protons are added at different times through the most stable intermediate to give the trans alkene.